Okay, everybody, we're back for the afternoon session. Watching Donna eat a really yummy donut over there. Sprinkles, yes. For those of you that didn't come in person, you're missing out on our fancy donuts. Okay, we're going to start up now this afternoon with Tony talking about our ocean model. Just going to share my slides here and hide this irritating screen. If I can figure out how to hide it.
You can do Control-Alt-Shift-H.
No, you have a Windows. It definitely will not be that.
It works on Mac.
Control, Alt, Shift, Control. There's no Alt button on here, dude.
There's no Alt? Maybe Command or something. Whatever.
Okay, anyway. Here, we're good now. Okay, Tony, take it away, please.
Thanks, Mike. So now we're going to take a closer look to the ocean component of ROCKE-3D. And how you're going to use this component really boils down to what kind of research you're doing or what kind of planetary body you're trying to model. So I'm going to walk you through the four different configurations. Maybe, Mike, can you go back to 2 or 3 slides?
2 or 3 slides. Oh, sorry. There we go.
Yep. So the first one at the top is we saw that earlier this morning with Costas, the prescribed SST or sea surface temperature run where you're going to couple to a dynamic atmosphere, a simplified where you have the value of the surface temperature for your ocean cell stored. And that's the only information that your dynamic atmosphere is going to get from the ocean at each time step. And while it's relatively computationally cheap, it doesn't give you a full picture of your climate system. The second one that Costas also described this morning is your Q-flux run, where instead of a file, you're going to couple to the dynamic atmosphere, a slab ocean, and you're going to compute at each time step the heat flux Q between the atmosphere and the ocean. Once again, relatively computationally cheap, but not as physically realistic as our third option, which has all the bells and whistles. It's our fully coupled dynamic system with now a dynamic atmosphere coupled to a dynamic ocean. And while it's the most physically realistic, it's also the most computationally expensive, because at each time step, in addition to your atmosphere, you're going to have to calculate things like the momentum equation for the ocean, the transport, the horizontal transport with mesoscalides, the vertical mixing, the tides in the ocean, etc., etc. And finally, the fourth option is at the opposite spectrum as our first case, where we had a dynamic atmosphere coupled with a prescribed ocean. Now we have a prescribed atmosphere coupled with a dynamic ocean. And that can be useful sometimes when you want to focus just on the ocean. You can just prescribe the atmosphere. Or in some cases, in our solar system, we have icy moons like Europa around Jupiter, or Enceladus around Saturn, where you have a whole ocean surrounded by a thick ice shell. So you don't have any atmosphere. So in this case, you will need to use a standalone ocean run. And so going back to something that Costas did as well earlier today, we're going to compare 2 runs. You can start with the dynamic ocean run PA1 SOM14, compare it, for example, to a Q-flux run. And one of the first things you're going to see at the top of your run deck is this host of subroutines that are dealing with all aspects of the dynamic ocean, from the momentum to the tides or the drag at the bottom of the ocean. In the second part of the run deck, you're going to see a slew of new parameters appearing. This one, K ocean equal 1, is really important for a dynamic equation. When you set this parameter to 1, you're gonna say to the ocean, okay, now I want a dynamic ocean. But you're gonna also see parameters to turn on different physical parameterization, like the coastal drag, or setting up your mesoscale diffusivity. Next slide. And finally, we also saw with Costas a few input files. These are used when you're starting a dynamic ocean run. The first one, OIC, is for the ocean initial condition, and basically you're going to describe the state of your ocean at the start of a run. It used to be a bit more complicated in Planet 1. Now in Planet 2, you can just specify the temperature and the salinity in each cell, and the model is just going to compute everything else in it, including the mass of the ocean in each cell. The second file is topo_OC. It's basically the topography and the bathymetry of your ocean. And in this one, you're going to specify for each cell the land ocean mass. And we have a binary mass, so we don't have any partial ocean land cell. So if it's set to 0, you're telling the model this cell is a land cell. If it's equal to 1, you're telling to the model this cell is an ocean cell. We also have host traits that you can use if you need. It's basically a list of cells that are straits, basically joining to mass of water. Next slide. And so a few things coming to Planet 2.0 soon, or that are already available for you. We've been working on the quasi-hydrostatic version of the model. The current version of the ocean model is hydrostatic, which was developed for Earth. So you can do a lot of approximation that saves a lot of CPU time. But in some configuration, when you're trying to model a deep ocean, and by deep ocean we mean ocean on the order of tens to hundreds of kilometers of depth, you don't have the right to use this assumption anymore. So this quasi-hydrostatic version of the model comes with a full treatment of the Coriolis force, as well as a relaxation of the shadow water approximation. Something that's already available is geothermal heating. You can specify a map as a net CDF file of the geothermal heating at the bottom of your ocean. We have more options for mesoscale diffusivity. So you go from constant mesoscale diffusivity throughout the ocean to something a bit more physically realistic with some exponential decay of your mesoscale diffusivity. You can now activate physical parameterization for the bottom drag at the bottom of the ocean, or coastal drag. We're soon going to implement some improvement to the sea ice thermodynamics, and in particular, an improved version of the radiative transfer through the sea ice. And something that could be interesting also for deep ocean is variable gravity. So on Earth, where the depth of the ocean is really small compared to the radius of Earth, on a body like Enceladus, where the ocean is a third of the radius, you can't consider the gravity to be constant anymore. It's you have an increase of the gravity between the top of the ocean and the bottom of the ocean. So all these options are either available or soon to be made available. And I think that's it for.
Okay, great, Tony. Thank you so much. Okay, I'm going to talk about a few other things in the run deck that should be of interest to many of you, and then Kostas will take over before we go into our last break for the day. So as mentioned before, again, many of these things have been covered in some detail by Kostas, as Tony pointed out, but repetition is good. sticks in the memory a little better. So that's the idea behind this. So, for example, if you want to change to a new type of world with a different kind of topography, there are a few files that need to be changed. One being, of course, the topography file. That's the topography on the land. This is the topo file. And as Tony was saying, there's a topo OC file. That's the bathymetry, or the topography of the ocean itself. So each of those files will need to be changed. And as I've said before, oftentimes we might have things sitting in previous papers that you can use, and usually those boundary condition files can be found in the repository. There is a river directions file that was required in Planet 1.0, but in the new version of Planet 2.0, this river directions file is no longer required. We let the topography decide what the river direction should be. In the old version, you had to tell the model exactly where the river should run between each grid cell, but that's been updated in the meantime. There's a name RVR file, and historically this has also had to have at least one name in the file. You had to name the river somewhere. I think this is no longer required. Then we have another feature in the model, which is called variable lakes. So this can be useful if you have a planet that only basically has limited amounts of water on the surface, and you let those limited amounts of water be lakes instead of oceans. What's interesting about using this, for example, let's say you set it to 1, so you don't want your lakes to remain static, but to allow them to come and go. Literally, it's the precipitation versus the evaporation in the model that will determine where the lakes actually should be instead of where you think they should be. So that can be interesting. But these model runs, just so you know, to come into hydrostatic equilibrium can take a very long time, so long that you may not want to wait for them. So you need to, again, think about your science case and how much time you think it will take for the model to come into equilibrium, which you can determine to some degree by talking with us. As I say here, if you need to generate new or remove given ocean grid cells, you also have to change the ocean initial conditions file. But as Tony said in Planet 2.0, this is a little bit easier than it was in the past. Then we have another file here called the GL melt file. And this is a file basically where excess ice that's built up on land can be moved back into the ocean, so you conserve your hydrological cycle. This can be very useful in situations where you have, let's say, a lot of high latitude land, and you know that you don't have, glaciers that are 10 kilometers or 50 kilometers high, so you can limit how much snow is allowed to accumulate in a given grid cell, and that excess snow will be moved into these what we call GL melt arrays that you define in the ocean where you should put them. But it's very important to note, and I have the same problem that Igor just mentioned offline a little ago, that I updated these slides, but the updates are not in here now, but they will be up for you if you refresh your screen. This GL melt thing is basically utilized when this WSN max has a non-zero value. So by default, it's set to 2 meters, which means that we don't allow more than essentially 2 meters of snow to accumulate on land. You can change this to any value you want. It can be 2 meters, it can be 2 kilometers. It's totally up to you. And that, again, that excess snow over that amount will end up in these GL melt arrays. But this should only be used with non-zero values when you have an ocean. If you do not have an ocean, you have got to set this WSN max equal to 0. So for example, in the case of a run deck where you only have lakes, you cannot use this feature. You have to set the WSN max equal to 0, and you have to let the model accumulate snow where it wants, because there is nowhere to put this excess snow, because your GL melt arrays cannot be defined in a non-ocean scenario. So keep that in mind. Mistakes like this have been made even in-house. People get forgetful about some of these parameters in the model because, as you've seen, there are many parameters in this model. These models are very complex. Okay, and as I can't see the chat window, but if you have questions, please ask in the chat. Okay, other things that you need to consider. So in the run deck, you can set the planet name. Say you want to give your planet a name like TRAPPIST-1c. You can put that in there, and that's something that will show up in the outputs as the model runs forward. Of course, as you might expect, For a given world, you might want to reset, the eccentricity or your obliquity. You can set things, as we say here in the calendar, which I'll talk about in a little bit more detail tomorrow, the sidereal orbital period and the sidereal rotation period. In a case where you have a tidally locked world, that's very easy. You set both of these to the same value. And you would set this thing called quantized year length to yes, basically, so that these two values stay tied to each other. I think Chris will talk about this a little bit tomorrow also, but the greenhouse gas file is one way to specify variables, but another way to do things is you can set a given value in the GHG file, and then you can multiply by that value in the run deck itself to these other variables in the next line. Like you said, CH4X equal to, whatever multiple of what is in the GHG file that you want to use. I think this is a little confusing. I don't like to use things like this. Frankly, I set these CH4, CO2, N2O. If I'm using them, I set them all to 1 and I put the specific values in the GHG file because I think it's confusing to put things in 2 places for the same thing. But some people love this, so we will never get rid of it. Which makes sense in certain contexts. But I think in exoplanet stuff, it doesn't make a lot of sense to have 2 separate things for the same thing. As we say here, physical properties of the atmospheric mixture, such as we'd already discussed, molecular mass, the mean molecular weight of the atmosphere, the heat capacity of the atmosphere, that's SRAT, that's CP over CV. Those all had to be set explicitly in this planet params _ mod F90 file that Kostas showed us a little bit earlier. And I would say for our solar system, as I say, in the present epoch, the only other thing that then orbital parameters is to change this thing called planet _ S0. That's the amount of insolation, the amount of watts per meter square the planet receives. So you have to put this value in watts per meter squared. So for Earth, it's around 1360 watts per meter squared today. But let's say you went back 1 billion years, you would have to change this to what the insolation was for Earth at that time. If you want to do modern Venus, well, you have to set this not to 1361, but to 2600, almost double what Earth is for these values. Those are a few things that you need to keep in mind. Okay, again, I changed the slide, but it's not changed. But anyway, we also have a single column model. We have mentioned this in our slides every year, but nobody's ever asked for it so far. There are very good 1D models available that are probably faster and actually have probably more features than our model have in many ways. But it is theoretically possible to run the single column model, a 1D model instead of the full 3D model. But again, it has not been used in recent years, so I'm not sure it's actually that functional at the moment. But if someone's really interested in it, we probably can find a way to make it work. But it would have to be a pretty good case to put some effort into that. But one advantage is that in theory, the 1D model could run in a laptop if you really want to do such things instead of needing a supercomputer. Okay, and the last slide for me before I turn this back over to Kostas is what to do in the event of a crash. We keep talking about these crashes that we've mentioned and things that might have to be changed in case of a crash. We have a Google document, which we try to keep updated, and probably as Planet 2.0 moves forward, we'll have to add additional things to this file. But if you have a model crash, this is the first place to go where you might find an answer to your question. The second place to go is, of course, to ask us. It could be that you push the model into an area where the model is basically unsuitable and has no chance of running. So again, please, if you have an idea for a new project and you don't see a template that we have run previously, then please reach out to us so that we can make sure that what you're doing makes some sense. Okay, I'll turn it over to Kostas now for the last bits before we take another break.
Okay, so we discussed a lot about model configuration and input and running it. So let's see what the model actually gives you as output. We touched a little bit about in those things, but we'll take it more systematic than that. First of all, the run ID is what we use again as a shortcut for whatever you name your model simulation. And you will always be getting a file that is called runid.prt. That will be in your output, and it is a very, very long file. text that essentially the model spits out every print star that you are doing there. And so it's the default model output, and you get all the diagnostic printouts that you have said, maybe debug printouts that you have said, everything. It's a very, very verbose thing, and this is the first place you should be looking at when you want to see how the model is progressing. And you can see even as the model runs how it gets populated. Then the model creates a file of the type that you see in the second bullet. By mon, we mean the 3 first letters of the month name, January, February, etc. And we keep that the same for all planetary configurations because why not? And then we have a 4-digit year, which can be suppressed and actually not suppressed, extended into 5-digit, 6-digit if appropriate, depending on the planet you're simulating. So if you simulate a planet with a 6-day orbit, then the years pass by really, really quickly. So you might end up needing more than 4-digit years in your simulation. But the default is 4. And then there is a dot, and then there is a collection of letters. They might be 3, they might be more. And I'll get to that in the next slide. And then it is the run ID.nc. So essentially the file name tells you the monthly mean, the month which contains the data, the type of file, which is a 3Z is there, the run ID, and the format, which is not NetSDF. I'll go into more details in the next slide. Then the model saves the RSF files that I told you with the KRSF variable that it saves every month, every year, every decade, whatever you want. And these are the really, really big files. Then the 4.1 and 2 files, which I mentioned quite extensively earlier, that you control their frequency with the NDisk variable. Then all of the model output that is actually useful for analysis, assuming that the model is running fine, is the ACC file. So going back to the bullet number 2, replace the ZZZ with ACC, that's your file. And it is, ACC stands for accumulation. The model accumulates diagnostics. It does not calculate means as it goes. So it just accumulates diagnostics, and then we have a utility called the scale ACC, which essentially scales the accumulations based on what they need to be scaled for and creates all the means. So when you run scale ACC, you convert essentially the ACC file into some more useful output that you can actually use directly for plotting. You can create means. So the ACC files are monthly, and you can create means with the utility that we have called some files. And you can make like 3 monthly, annual, decadal, millennial means, whatever you like. This utility is smart enough to be able to name your output files in a way that makes sense based on what you are averaging out, assuming that you are averaging something expected, like not a March with an October and a January of the next year. So yeah, I think that this will freak it out. But if you do a regular mean that is something reasonable, then it will know how to name. We have another utility, and for those utilities, you probably have already compiled them if you follow the instructions all the way to the end that we've sent you. It's called diff report, and it is a homemade utility that essentially compares NetCDF files, but not just doing a diff between 2 files, because the 2 NetCDF files will differ because they have some metadata that are different. But you can compare, it only compares the actual data. So if you have 2 simulations that you have changed anything, you have not done any changes, only you change, for example, a compiler version. You want to see if the results are exactly identical. You run the model with one compiler, you run the model with the other compiler in using 2 different run IDs, and then you compare the 2 output files, NetCDF output files with diff report. If they differ, it will tell you how they differ. If they don't, then it will tell you nothing. And it's an extremely useful utility, especially when doing debugging. Then we mentioned early on Panoply, which is the tool that we have developed in-house to make to plot output of gridded data. And it is quite generic, and it is very useful. Many people use it outside GIS, and it is extremely common that you go to a conference and you see plots on it. It's actually every time I see that, I really enjoy it. And so it's extremely useful, very powerful. It even has some basic scripting functionality that you can use to create multiple plots, movies, or just create a configuration that creates the same types of plots from different outputs. So it's extremely useful. I recommend you to at least take a look at it if you are not already familiar with how to easily plot NetSDF files or gridded files in any way. And then NCView is a very basic functionality on Linux that you can see quickly the model output, gridded output again. And it's not making publication quality figures, but it's the fastest way to see something right on the spot without transferring files anywhere. Or if you just want to see, the pattern of something, if something looks very reasonable. Okay, next one. So I mentioned that the ACC file can be scaled by this scale ACC program. And it has a lot of different, it can create a lot of different outputs. So the ACC file contains what we call the AIJ, AJ, AJL, AGC, etc. And by a lot of these letters are not random. A means output of related with the atmosphere. O means output related with the ocean. And then I, J, L are the three dimensions, the three spatial dimensions: longitude, latitude, altitude. So the AJL contains the zonal mean file output of the atmosphere across the latitude and altitude dimensions. And if you go halfway in the bullet list, there is an AIJ and IJK, which is saving output in constant pressure levels. I think this does not exist anymore because everything is in AIJL now. But for client 1.0, it certainly is there.
1.34.
Yeah, but
it might be on the
I think so.
yeah, it is, but we're moving things into AIJL. So in AIJ. So there are a lot of, if you want constant pressure relative humidity, for example, you can find them in AIJ as well. Oh, okay. One thing to keep in mind is that when you have topography and you are seeing things at constant pressure levels, you might end up with missing data, and that is by design, of course. If you request temperature output, let's say on Earth, let's say 800 millibar, then when you are around the Himalayas, there is no such place. You're underground, so there is no output. So if you see that, don't be surprised, it's expected. And AIJL is following the topography, the different layers through the sigma coordinates of the vertical layering. So there will always be there. Okay, next one. So yeah, I'm not supposed to be reading these. You have access to the slides and you can refer to them. The important thing is that when you do the scale ACC, so the letter T here stands for tracers. So like you said, the bottom of the list. And I guess I stands for ice. I've never used that file myself. So the important thing is that when you run the scale ACC program, you essentially type scale ACC, then the file name, the ACC file name, and then you need to type which of those files you want in the output. So if you want the AIJ file, you say scale ACC space the ACC file space AIJ, and that's it. If you want multiple, you comma separate them with no spaces. So aij, comma, aijl, comma, etc. And if you want really everything, instead of separate naming them all of them, you just say all, and that's it. So I think that for exercising, if you really want to see how this model output looks like, it has a lot of variables, and we take pride of that because nearly anything you might want is there. It is extremely seldom that you will not find something in the output. It means that you are either asking something extremely detailed, or you just made some code development and you need to code in your own diagnostics. So I would say that an extremely nice exercise for you to do, maybe after we're done today and have questions for tomorrow, is to follow the instructions that we gave you, run the model for just 1 hour, like the setup hour. You don't have to go beyond that. You will see the partial file that Mike mentioned, which is the output of the first time step. So just run scale ACC on that because it is an ACC file. Run the scale ACC, you will get the output, and then take Panoply, NCView, or your favorite NetSDF viewer, explore the output a little bit, and come back with questions. You will have plenty. Okay, and then, yeah, keep those 2 slides somewhere handy because they really explain you for the output, what type of output is available. This changes in the future in Planet 3, but we're not there yet, so no need to mention that.
Last slide.
Yeah, and then I'll start from the bottom here. If you want to add diagnostics and the output, the most probable place you should define them is this file, the defacc.f. And by define them, I mean you need to say that I'm going to create a diagnostic with this name and these dimensions and this frequency, or some basic. This will be the short name and the long name in the output file in the NetSDF. These are the units. Just literally define what will show up in the NetSDF output. And then you need to go into the code and actually populate this diagnostic with the values you want. And that, where this happens, depends on what type of diagnostic it is. Just because we have so many diagnostics in there, it means that you will most likely have an example to follow. So if you want to print, for example, the third quartile of daily mean temperatures across the model, we have a diagnostic that is printing the maximum daily mean, the maximum temperature over the day. So you can follow that and just change the calculations where needed. I mean, if you write some code and there is really no example of any diagnostic of that sort, I don't think I've ever encountered that. Yeah, then we chatted a bit about the Planet Params mod, and we will talk about that more later tomorrow, because this relates with the creation of the actual planet, where it stands in the stellar space. And then there is another one that is called constants mod. It literally contains the constants that we are using, like pi, and the gas constant, true constants. And then in general, the recommended way, if you want to write new code, is, let's say you have a new functionality that you're adding, so you know how to name it. This is a triple X that you see there. And then there is a com component, which is essentially a module that holds the variables that you need for your new code. And the DRV is the driver that links the main model with your code. So if you have functionality that is, it says, I don't know, escape, like atmospheric escape, say you are running a code for that. You should not be doing it with this model because escape happens outside our model domain, but just in the sake of the example. So you have a file that is called escape_com.f or F90. And then that holds all it's the module escape that holds the variables that need to be known across the model. The escape_drv is the file that creates the links between the actual model. Actually, it says it is used to call the escape functions. And then any other escape underscore whatever files, that one or many files you have, will contain the actual calculation. And an escape is easy. It's like a few lines of code probably to code it in. And so you might not need all this big functionality, but for larger modules that you might be including, and then it's this is how it works. And you will see, the PBL, planetary boundary layer, the clouds, the radiation, all these loosely follow that infrastructure. And there is even a model underscore com, and so there is it's not we're not 100% consistent, maybe not even 80%, but we are trying our best to follow that. Last but not least, we have CPP directives, so they can enable or disable large or small pieces of code. These are the things that are named as hash defined at the very top of the random. So what really happens is that as the model compiles, it is parsing the random and sees which things need to be defined with this hash define command. And then when it compiles every individual Fortran file, it scans the model, the C preprocessor is scanning the model and enables or disables pieces of the code. And this happens only in files that you have included with this line at the top of your Fortran file. So in essence, when you create a new file, if you have no relevant defined statements, you don't care about that. But if you start saying define this or define that inside your model's source code, you need to have this include randomops.h so that the actual Fortran code is aware of which things have been defined in your run. I think that's all I have.
Okay, great. So we're going to take a break here. And then for the last bit this afternoon, it's just a question and answer session. So any questions that the online or in-person folks have, we will do our best to answer them based on what we learned in theory this morning. If there aren't any questions, we will end early. Some years there are not many questions. So we'll come back here at the top of the hour in about 20 minutes, and we'll hold a bit of a Q&A there if you all have Q&A left over. We've been trying to answer in the chat window as much as we can, but we see how it goes.
And it can really be anything. I mean, we'll have a Q&A also tomorrow, I think. But if you have a question that, like, hey, here's a case I want to simulate, can I use this model? I mean, we can take that today. I mean, just ask anything. It's your time. You will not find us easily in the same room able to answer questions. So this is your time.
No, he's wrong. You will never find us in the same room answering questions like this, except at this tutorial. This is your chance to ask questions, especially those of you that have used the model previously. This is the time to ask us questions. So anyway, we touch back in a few minutes, and enjoy your break. Okay.
Can you answer the question about organic outguessing?
I do.
Oh, you did already.
Yeah. Unless
Okay, everybody, we're back again. I'm just putting up what our plan is for tomorrow. So you can see that. And I should, again, I thought that I changed this, but I'm going to cover this because Tom Clooney's on vacation. So we'll talk about the calendar tomorrow. Igor will talk about ground hydrology. Eric Wolf, our radiative transfer expert, will come and talk to us about the radiative transfer. Vincent Kaufman will come talk to us about this tool called Planetary Spectrum Generator and how it interacts with ROCKE-3D. We'll have lunch, and then Chris Colosso will come and tell us how to create a new planet, and then we'll again have a Q&A. So you don't have to have any more questions. We see you've asked a lot of questions in the chat, but it's up to you all. So if you have a question, I would suggest, let me stop sharing my screen, and then we can see if you have a question, you could raise your hand if you want to ask in person. Otherwise, if you want to put it in the chat, that's also doable. So do we have any questions?
So there were a list of alternative scale solutions, like A dire,
Yes,
A reg. How often do you use those?
it depends on the person.
Yeah.
So for me, I'm always looking at the AIJ, AIJL, TIJ, TIJL, TAJL, and maybe AJL. So essentially, 2 or 3-dimensional atmosphere or tracer outputs. I was chatting recently with Clara Ove just to see some dynamics changes in some planetary runs that I have done, that I have enabled some passive tracers that diagnose dynamics of the atmosphere, like circulation and related stuff. And she told me, oh, everything you want is in the AJC file. I was like, I have never, ever scaled it in the past, not let alone look into it. And she was like, that's the only file I use. So,
It has a
So
stream
it-
functions. in it.
yeah, so it depends on the person. And then I was thinking of some ocean diagnostics. I think it was the Southern Ocean circumpolar current or something. I don't remember something. And they told me, oh, it's in the OIJ file, and I had never scaled that file in the past. So it really depends. If you want to simulate to see what the jet stream is doing, for example, you might need the 3-dimensional ocean output. I don't know.
But normally, I guess people should start from AIJ file. It's the biggest one and it has most useful diagnostics.
The biggest one is speak about the atmosphere. TAIJ has 7,000 values.
The-
TAIJ.
Well, I probably never looked at it.
Yeah, exactly.
Well, actually, maybe, yeah, I did look at it, but yes, it's just
No, it's,
unusable.
yeah. So AIJ is the #1 place to go. So,
Yeah, and I think in our pre-tutorial instructions for installing the model, we have you generate scale ACC on the partial file for the AIJ file. So that you could use Panoply to look at the surface temperature, for example. That's the most intuitive thing for most people using GCMs.
Yeah, and if you scale partial file, keep in mind that it's just one time step. So a lot of things have not yet been initialized. In particular, all radiation diagnostics will look weird because half of the planet doesn't have any radiation yet. So it basically was just gray parts. But whatever was initialized, it should have some reasonable values.
Okay. Any other questions from our audience? Oh, we have another question in the room.
So, like maybe open this like def ACC startup and maybe like walk in sample. I've been looking at it and I'm not really all the time.
I can do that. If you want.
It's very technical.
I mean, it's like 3 minutes.
Okay. That's
No,
interesting.
NNC is not very difficult.
You just need to copy what's been done for.
Yeah, I just
There is
wanna-
one.
if you can show me like how to choose.
Why don't you share your screen?
There is one little trick that you need to know. But other than that, yeah, it's pretty straightforward. So I'll share my screen. I'll just take a totally random example, okay?
Yeah, that's fine.
So here's the def ACC file. I went in some random place into this file. And let's take this block here, okay? So this block says K equals K plus 1, which means I am now defining one more diagnostic. This line is key. It is saving the current value of the current index into a named variable in Fortran. This is what you should be looking for in the middle code. Then you define things like the short name, the long name, the units. I have no idea what this title is. A scale is
Short title.
I don't know what that is. This IA rad says how frequently to sample it from in the model. So this is a radiation related diagnostic. So you should be sampling it only when the radiation is cold. Oh, we haven't discussed about any of that. And so you know, and depending on the diagnostic, you might need to define a few more things or a few less things here. So why I said this thing is important, it's because this variable is the one that communicates with the rest of the model. So if you go in the model and just grab the code for this variable,
So it probably would be more convenient to use IJ diagnostics rather than J.
doesn't matter. I mean, it's only 3 lines. It's the same thing. The
Okay,
idea is the same.
I guess just J diagnostics are more here because,
No, it's fine. It's fine.
Yeah, this is.
okay.
Oh, by the way, yeah, this one is not a very good example because it is used in a more generic way.
But that's what I'm saying, just take
No,
any
it's-
AIJ.
Okay, IJ,
That's not there more like straightforward.
okay, let's take the ocean fraction. Okay, is that
Oh, it's
okay?
also J.
IJ.
Ah,
I'll take this.
okay, yeah.
So, I mean, the same idea, you define it in some way. And then the important line of code is essentially this. Not the period, I think it's this one. See, when you take random variables, you can know exactly. Let's take it.
Just take surface temperature, something trivial. You
Yeah, no, I don't want to take the fractions.
yeah, because all those ones,
Yeah, precipitation, IJ.
yeah,
So precipitation, okay, something that everybody understands. IJ prep equals K, that's an important line. Precipitation is the diagnostic name, that these are the units, this is the, sorry, this is the diagnostic name, this is the long name, the units. It is sampled at every source time step. And you take this thing, which is the variable that uses it in the model, and you grep it, and the key line is this one, this last one, which says in the AIJ diagnostics for the grid I and J related with this diagnostic, accumulated, which means added on top, and then the variable that you should be adding is PRCP. And PRCP is calculated somewhere in the code. So you know that you want to diagnose this PRCP variable, and you save it in the AIJ array with index IJ prep, which has been defined in the basis. It's it has one extra hop from what you might expect, but it's straightforward. You follow this the example.
So I just need to find the right. Variable like AI there.
yeah, basically there are 3 places where you write that in the diagnostic. DFACC, you add that section. Then in Diag home, you actually add just one variable, which is that name that you use, like which is equal to K, so that it's basically declared. And then in the real physics code, you add this line AIJ, something is equal to AIJ or something plus whatever you want to operate. So that's kind of a minimum way to define the data. Of course, you have to know it.
Yeah, yeah.
Yeah, but that will come years.
Right. I have a.
Yeah, if you are looking at this, it's different. Yeah.
But it's not.
It's, yeah, it's some.
You answer the question.
Okay. I answered a question from Aliyah in the chat. Yes, as you go to higher gravities, I'm certain you will come into problems. We've had problems in the past, but we have not explored this recently.
Then
So-
we went up to, I didn't know we went successfully to cooking that.
I tried it recently, it actually worked, and I was
Okay.
surprised.
Okay, yeah, I was still behind in less than 2.
Yeah.
So that, yeah. Okay.
Was it crashing in the ocean? Or it didn't?
No, it was crashing in the PDL, I think, as usual. Or claimed to be crashing in PBL.
Oh,
Probably
PBL was the
somewhere
place
else.
that we was catching the fatal error.
Yes,
Yeah,
exactly.
it's still atmospheric.
So yeah, that's an important thing to keep in mind. If the model crashes in one place, it doesn't necessarily mean that this is a problem. It might be the place that it could not continue further.
Yeah, in comparison to these traps, sometimes fails to find the place where the model actually crashes. So not always.
Okay, any other questions online or in the room? Don't be shy.
Yeah, I mean, you can speak up the questions. So for monthly mean outputs, I will just reply verbally to the question in the chat. So the monthly mean output is always there. And you cannot say that, hey, I'm running the model with, actually you can say, I mean, I'm running the model with no output, but not with partial monthly mean output. You cannot do that. So if you want to, if you know how long it will take to calibrate and you really want to suppress as much output as you want, as you can, then you can completely suppress the ACC output and then after 1,000 years or whatever, turn it on with the I file and start getting output. But getting samples, so only small pieces of the output just to see radiative balance and then enable, no, you cannot do it. There is a way to take sub-monthly output and that you can suppress it or enable it at will, but not for the monthly.
Yeah, another thing you can do if you want to save some space and you don't need to see monthly output is that you can use another run deck parameter called nmonav, which I'll put here in the chat.
Yeah, that's a good idea.
And that variable you can set to how many months you want to average over, and that is what will be output. So you can set this to 12 months, then it will write out just annuals. So every year you can set it. I recently set it to 10 years.
Or if you have a very short orbit.
Yeah, so I had a planet where I had an orbital period of 4 days, and it generated otherwise a lot of output. That planet, I ran 35,000 orbits. So I did not want all that data to fill up my file system and actually drive the IO on the supercomputers mad. So I only had it writing out every 10 orbits, basically. And probably even that was not, should have made it like 100 orbits.
Can you modify that on as the model runs?
You can stop
Okay.
the model and you can change it in the I file how you like.
Okay, so in that case, if you are just exploring how the equilibrium of the model, then you can save like annual outputs, and then when you are happy with the annual means, you enable monthly output.
Yeah, I mean, that's one thing that maybe we'll touch a little bit on tomorrow, but we recommend for an Earth-type planet, if you want to see if the atmosphere is equilibrium, you should do a 10-year average at the end of the run. And you look at a variable that you can find in the AIJ file called net_planet_, or sorry, net_rad_planet. If that value for 10 years is within plus or minus 0.2 watts per meter squared for an Earth-like run, we consider the model to be in equilibrium, meaning the atmosphere is in equilibrium. I think we do discuss that tomorrow. Other models are not as strict as we are. I have seen values.
I see the slide. You have
1 or 2 watts per meter squared, but yeah, we'll discuss this a bit more tomorrow. But that's an important thing to think about when you run your model and you're looking to see if it's in equilibrium. By the way, this does not mean the ocean is in equilibrium itself. That can take much longer. I've seen model runs that came into equilibrium in the atmosphere in, say, 500 orbits, and it took the ocean 7,000 orbits to come to full equilibrium itself. So again, it depends on the science you want to get out, how long you have to run the model. But since most people are interested in the atmosphere, the time to equilibrium is much shorter than it is in the ocean. I don't know if you want to add anything.
The shortcut for the ocean is that if you really want to speed things up, you just make it shallower. But depending on your science question, you might not have the ability to do that. So,
Exactly.
but this is a key thing to consider. If you don't know how shallow or deep the ocean is. The shallower it is, the faster it will equilibrate. The deeper it is, the more interesting results you will get by being.
Depends on what
diverse.
physical
But,
processes you want to model.
It depends what you want to model.
Typically for our Earth run, and the ocean is on average 5 kilometer. Yeah, we need 6,000 years to get the ocean into equilibrium.
Yes, thanks. Downloading data from now. Yes. Yeah, we have some in-house scripts that we have written to look at the post-process data. We find in some runs we never reach this plus minus 0.2 watts per meter squared, but it's very dependent upon the situation that you're modeling, whether or not that is a good diagnostic to use. For Earth-type planets, we find that this is a reasonable value, but I've seen cases where we have limited water on the surface. We only model the lakes, and those can take much, much longer. It takes a long time for the hydrological cycle to come into equilibrium.
The lakes for our CF6 runs needed at least 5,000 or 6,000 years to celebrate.
So again, it depends on the science case, depends on the setup that you're running, what equilibrium means. If you're not certain, write us. Try to give you some guidance on what's right. It'd be a shame to publish something that's not in equilibrium that was really interesting.
Well, for certain science questions, you might not care. I mean, if the groundwater is not in equilibrium and you're studying surface air temperature, you're probably okay.
It depends.
If the
It
other
depends.
things are in equilibrium.
It depends on how cold the model is. For example, it might not be equilibrium because it's still dumping snow in the poles because you have a low liquidy world. And that will take a long time to come to equilibrium. By the time it finishes in equilibrium, all your water might be up in the poles.
But you will see that in the atmospheric
If you know what to look for.
Yeah.
The complex model, as we keep saying. Let's see. Yeah, you would want your N monav to be a multiple of 12. That would be recommended. Yes. Yes. I don't know if you set KRSF to 1, if you'll get a restart every N monav. I don't know the answer to that question. I'm sorry. I've never ever set KRSF to 1. So I'm afraid I don't know the answer to that, but you can do a test yourself. It wouldn't take long to find out.
Is there ever a reason to use the accumulation file directly? Does it have more information before you do those averages, or it's just like an intermediate state of averaging? When you need to first process it together.
It is an accumulation file for a reason. And the reason is that making averages depends on a number of things, including primarily the number of days on that month. So it's not like 30 days every month and then you divide by 30. And when you want to make longer than monthly means, then you need to take into account the duration of accumulation for every period. So if you already have the monthly mean of February and of March, the monthly mean of the two is not the two of them divided by 2. So if you have accumulation files that contain the information of the durations, it is easier to create a new accumulation file for that new duration and then scale it to get the mean. And there might be some additional reasons for that, but I think this is mostly the case. It simplifies post-processing if you want something at a higher than monthly mean, or even the mean itself.
Yeah, I guess just scripts become more straightforward.
Yeah, more generic scripts you can have. So you can use it. I mean, I know of people using directly the ACC files and making the means in their scripts because it is faster and you don't have to create the additional files and less files in your file system. But really, if you do an NC dump of the ACC file, it's very good.
I mean, if you want to do that, you would want to talk to some people in this building offline. It's better to use the scale ACC.
Yeah, scale ACC is simply it creates something that is human real.
Good questions. Okay, any other questions left? Before we call it a day here? And the chat is quiet. Okay, well. Assuming, let's see this one. Okay. For simulation, yes, it was an M40 resolution, absolutely. I'm not sure if it would, well, Tony could tell us, maybe it could take longer. You said 7,000 for runs that you're familiar with for the ocean, but was that for F40 or M40?
That was for the ocean. That was 1.25.
So F40.
Yeah.
For F40. But I see the same for M40 simulations, that they take about the same amount of time.
But obviously it will take less in real time to run.
Yes, it will take less time to run the M40 than the F40 in all situations. Again, think about your science case for the resolution you want to run. Don't go running F40 unless you really need it, because it will take much, much longer to run. Let's see, the ocean depth matters more. Oh, yes. There's a big heat capacity. Yes, it does. Think about, anyway, if you have more questions or more questions come up after you have slept on it tomorrow, please ask them tomorrow. Anything we've covered today can be asked about tomorrow. Anything covered tomorrow can ask about tomorrow. Anything not covered that you're curious about can be asked also, of course. We're happy to ask questions, answer questions as much as we can.
So if you are in this tutorial because you know of a case that you want to simulate, you can ask about it.
Yeah.
Now is the time.
Please do.
Now or tomorrow.
Or if you don't want to share your secret case, you can, to everybody, you can write us, directly. Can tell. No problem. Yes.
The tradition, like common earth tuning parameters, so that stuff about, say, like cloud ice versus snow. You guys like need to mess around with
No.
those parameters, you just leave them fixed when.
We do not touch. All of these models have been balanced from modern Earth. We cannot balance them for basically any other planet except maybe Mars, and only Mars for a given season. So we
Well,
cannot,
balance the Mars because it has no clouds.
well, also,
Yeah.
yes, but
Okay,
we couldn't do that. We couldn't rebalance the model for an exoplanet because we have no idea what the actual numbers are. So no, that's one limitation of these GCMs using them for non-Earth planets, is that we don't have any way to really adjust the model for that particular climatology to get it right. So this is sort of a best guess.
You just trust your parameterization.
You ever like prefer those values, you know, like a lot of control over
We have done a lot of tuning for the planet to run the templates. And we present some results about how much these things matter in the paper that we're finalizing. But we don't do it systematically because these are, tunings in uncertain parameterizations. It's not that you are calculating something from first principles and then, then you have a number. You literally tune something because it is not
Right.
parameterized.
It's a black hole.
It's a black
I had to
hole.
do it last year for some runs I was concerned about that I was a bit surprised by the results in Planet 2.0, but I quickly realized that this was a no-win situation, and I didn't achieve what I had hoped to achieve. So there's always
You just don't have, and you will probably never have the enough data to do it for our time. And then think of how we do it on Earth, right? We take a simulation for this prescribed sea surface temperature, which means we know. And then we tune a couple of things, or maybe 5 things related with the clouds, in order to make proper cloud cover, which maybe we will get one day, but like right now, direct imaging is 1 pixel for a cloud, so you don't know anything. And then we also tune it based on the incoming and outgoing radiation, which we will not know from now. I mean, we might know what is going in at the top of the atmosphere, but how much is coming out or how much is absorbed. These are numbers that are really hard to get from telescope. So we just not have, with this generation of models or scientists even, we will not have this information up.
We have a time dependent spectrum,
Yeah, we can do that.
spectra, yes, but how will the spectral files change for that?
So,
How to calculate,
so the model has a spectral resolution. And the input file of that spectral resolution can have a time dimension. And we get that, so for the sun, we have measurements that we measure the sunspot cycle, for example. And then we know the spectral dependence of that change through the 11-year cycle. And we use all that information as input for the spectral resolution that the model is requesting. For any other star, we can do the same. It's, I mean, you just need to essentially, in order to reproduce a spectrally, a temporally changing spectra, you need to use master year equals 0, which means that you are running the model in interannually varying mode instead of repeating a climatology. And then you need to set the greenhouse gas file that has, you know, either one value or multiple values that are the same or changing, whatever. But the way to change the, actually, no, you can change the solar spectrum, the spectral dependence by itself. Okay, I take back the master year. But you can hold that in. I mean, if you have information from another star,
but you have to
No.
run socket for each.
no,
I don't understand exactly that part.
no. The stellar spectrum is what happens outside the model's atmosphere. So it's
Yeah, yeah.
just plain input.
But the spectral files. Are
The
for
spectral files, no, this, okay, I see your question. So the spectral resolution of Socrates or any radiation stream is needed in order to resolve the amount of radiation absorption, for example, that happens into an atmosphere of a certain composition. So for for each one of those bands, you need to know how much radiation is landing at the top of the model per spectral bin. And then Socrates will do the calculation inside the atmosphere related with the absorbers in the atmosphere. Still, you need to have the stellar input as an external file. And that can change with time, and it needs to have the same spectral resolution because there is input in the model, but the actual calculations of Socrates are independent of what you are using as external input at the top of the atmosphere.
Okay, we've answered a few more questions in the chat. Okay. Any other questions in the room?
Are you answered?
I think so, yes. Okay, great. Assume that's it for the day. Thank you all for tuning in. If you're in a distant time zone, I hope you have a good night's sleep. And we talk to you all tomorrow. I'm gonna go ahead and stop the recording.